Before we finish up our discussion of types of chemical reactions, we need to take a look at one more specific category of reactions known as oxidation-reduction reactions, or combining the beginning portions of both of those terms, redox reactions. The read coming from reduction, the ox coming from oxidation. So let's take a look at what a redox reaction is. These are reactions which involve a transfer of electrons between substances. So we're looking at here electron transfer occurring whenever we are examining redox reactions or redox chemistry. So we need to unpack what is an oxidation, what is a reduction. An oxidation is a loss of electrons. If a substance is being oxidized, it's moving to a more positive state or, in some circumstances, a less negative state. In either case, the only way you can make something more positive or less negative is to remove electrons from it. I'm giving you two examples of oxidation processes. One that we were quite familiar with when we were looking at ionization energy values. You can take a neutral sodium atom and you can remove one electron from it. That would be an oxidation. The sodium atom is losing electrons. In the process, it becomes a +1 ion. So sodium is moving to a more positive state here in this oxidation. In our second example, we're starting out with a cation that is already positive, the iron 2 ion, but we can remove an electron from it, oxidize iron 2, and convert it into the iron 3 ion. So both of these processes here represent species that are losing electrons. And I also want to point out, before I move on to reduction, that we can look and that we can see that these equations are balanced not just by mass, but also by charge. There is a neutral charge on the sodium atom on the reactant side, and if we take a +1 and add it to a -1, we also have a neutral charge on the product side. Iron +2 charge, adding up the +3 and the -1, we come up with a +2 charge on the product side as well. So the point that I'm saying here is that they are balanced. Both of these equations are balanced by mass and also by charge, which is necessary when you are writing chemical equations. Let's take a look at what a reduction is. If an oxidation is a loss of electrons, then by deduction we can suggest or propose that a reduction would be a gain of electrons. So oxidation, loss of electrons, reduction, gain of electrons. The substance is moving to a more negative or less positive state. And here are two examples of reduction processes. Here is a neutral chlorine atom. We're giving it one electron to form the -1 chloride ion. So chlorine is gaining one electron, becoming negatively charged. We reduced the chlorine in this process. In the second example, I'm starting with a copper +2 ion. I'm giving it one electron and forming the copper 1 ion. So this would be an example not where you're forming a negative ion. Copper 1 is not an anion, but it is less positive than the copper 2 ion. So the only way to make something less positive is to reduce it, to give it an electron. And again, quick check here with charge, the +2 and the -1 adds up to a +1, and that is the same charge that we have on the product side. So I'm looking at both of these equations and seeing that they are balanced not only by mass and also by charge. The last thing I want to point out before we move on to a further discussion is that oxidation and reduction must occur together. You have to have these processes linked. In other words, you can't oxidize a substance without at the same time reducing some other substance, because the electrons don't just appear and disappear out of nowhere. They are matter, and we have to conserve matter in chemical changes, so we have to account for where the electrons are being transferred to. If something's losing electrons, something else has to be gaining them. There are a couple of acronyms to help memorize this process of oxidation and reduction. This first acronym is the one that I was taught when I was learning this for the first time as a chemistry student long ago, and it is the acronym Leo the Lion Goes Grr. And the blue Leo and the blue grr are letters which stand for words. So Leo, loss of electrons is oxidation. And then by deduction, grr, gain of electrons, is reduction. So it's a memory device here to help you keep straight. Is oxidation the loss, or is it the gain of electrons? Well, this acronym should help you be able to figure that out. Loss of electrons is oxidation. Gain of electrons is reduction. A couple of years ago, a student in my class suggested that they were taught another acronym, and if this one works better for you, then absolutely embrace it. Science is the study of what works. So here is a second acronym, oil rig. And hopefully looking at the letters in this acronym, oil, oxidation is loss, rig, reduction is gain, referring to electrons. So this is a second acronym to help you remember that oxidation is loss of electrons, reduction is gain of electrons. I personally prefer lions more than oil rigs, and since I was taught this first, this is what sticks in my head, but please choose what works for you and use it. Let's do an example of redox chemistry looking at a type of reaction that you are already presented with. So we talked about the 5 types of chemical reactions that you should know and be able to use to predict products. Single replacement reactions was one of those 5 types. And note that single replacement reactions are example of redox reaction or redox chemistry. And let's take a look here with the example that we discussed when we presented the idea of single replacement reactions and discussed what they were. We used this example in that discussion. I see magnesium, a metal, reacting with hydrochloric acid in solution, and I'm not noting those states just to keep the equation a little less crowded, because we're going to write some other things as well, so I'm trying to keep it a little clean. We understand in single replacement reactions that the magnesium is going to replace the hydrogen in hydrochloric acid. So on a quiz or an exam, if I gave you these reactants and an arrow, based on your knowledge of types of chemical reactions, you should be able to predict the products. Magnesium will replace hydrogen in the compound, and hydrogen will now be an element. And of course, it's a diatomic element, so I'm noting that. It's a gas. The magnesium will now pair with chlorine in an ionic compound, and you will get magnesium chloride, writing the correct chemical formula for magnesium chloride. You have to know, of course, from nomenclature that magnesium will always form a +2 cation in a compound, and chloride is, of course, the -1 anion. Many times students will incorrectly tell me that magnesium is a +2 ion as a reactant. But this cannot be the case. This cannot be true. The only substances that are stable in nature are neutral. So all elements in their uncombined elemental state have to be neutral. So the magnesium metal is neutral and has no charge as a reactant. I know that HCl is a polar molecule. I know that hydrogen is partially positively charged and chlorine partially negatively charged. But for the purposes of redox chemistry, we just kind of simplify, and rather than saying partial positive and partial negative, we just sort of assume for bookkeeping purposes to make this picture cleaner that hydrogen is +1 and chlorine is -1. But again, that's a bit of a bookkeeping, in other words, not a physical reality, but just helping us see and understand what's happening here. So in order to understand redox chemistry, you have to take a look at charges on atoms exactly as we were doing here to make sure you can evaluate, or to help you evaluate, whether something is changing its charge. If it changes charge, electron transfer had to occur. So the only species that I have not noted a charge with is hydrogen as a product. And of course, it's an element, so any element has to be neutral in its uncombined state. Magnesium as an element on the reactant side is neutral. Hydrogen as an element on the product side also has to be neutral. And now that I have filled in charges for every one of the atoms or elements here in this redox equation, I am now in a position to evaluate, did any substance get oxidized? Did any substance get reduced? And I already indicated that single replacement reactions are examples of redox reactions. So we're expecting that answer to be yes. Something got oxidized, something got reduced. Well, oxidation is loss of electrons. A substance is moving to a more positive or a less negative state. And examining, did anything move to a more positive state on the product side compared to the reactant side? And the very first substance I'm looking at, magnesium, that answer is yes. Magnesium starts out as a neutral element, but it ends up as a +2 cation in the compound magnesium chloride. So I'm going to put little arrows here connecting, right, these two species and say along the line magnesium, right, is reduced. Oops, excuse me. And magnesium is not reduced. Just as I said, magnesium gets oxidized, right? It loses 2 electrons and forms the magnesium +2 cation. So magnesium gets oxidized. Well, if magnesium is losing electrons, where did those electrons go? Because as we stated, oxidation and reduction has to happen together. So what substance gained electrons? What substance moved to a more negative state or less positive state? I can see here that chlorine did not do any change. Starts out -1, ends up -1. So we can pretty quickly eliminate the chlorine species as the candidate for reduction. So that must mean hydrogen is our only choice left to undergo reduction. Looking at hydrogen and HCl, it's +1, but I see that it ends up in a neutral state. The only way to take hydrogen from a positive state and convert it to a neutral state is to reduce the hydrogen. So looking here, I can say that hydrogen is reduced. Right, so H plus is reduced and you form H2O, or neutral hydrogen atoms. So the hydrogen ion is gaining electrons to form neutral hydrogen atoms. Where did those electrons come from? They had to come from the magnesium atom, which is getting oxidized, losing 2 electrons. So we have here an example of redox chemistry, oxidation reduction happening concurrently between the magnesium and the hydrogen ions in this example.